Okay, now that I've drawn some extra stuff to help me get away with this one, in this video we're going to talk about X-ray reduction. So last year I showed you a little bit of this, but slightly more detail, obviously from the wicked picture and super awesome graph. I'm going to talk about three main concepts and unpack them a little bit as we go. So the first one, bremsstrahlung, which is another word for continuous range of frequencies produced in an X-ray machine. We're going to go through how to derive the maximum frequency for an X-ray that could be produced, and we're going to talk about characteristic peaks and where on Earth they actually come from. So, first of all, bremsstrahlung. Now, as your electrons whiz towards a target material, so we've got a target material like this, so this is the surface of this target over here, so here's our target material. We're looking at the nucleus, so positive charges. As we have this thin-ish beam of electrons whizzing through, we've got a random sort of scattering of X-rays as they come through, and we've got a random setup of nuclei near the surface and kind of that crystalline or lattice metallic bonding type structure. And as these electrons come through, they're going to be accelerated. And as they accelerate, they're going to lose energy, and that energy that they lose is going to be given off as photons. Generally, we're looking at high 90s, so let's go 98% is heat. That's probably a little bit more, maybe a little bit less, and the 2% that's useful is hopefully going to be somewhere in the X-ray bands. So visible light is about that many electron volts, usually about that many electron volts. Here we're talking about that many thousand and up, so we're looking at 10 to 15,000 generally, through to a few 100,000 electron volts is considered somewhere in the X-ray spectrum. So we're looking at awfully huge amounts of energy here, guys. So as these electrons come through, they will be attracted towards and sort of bend and sort of do all this on their weird kind of paths through the nucleus. And each time they bend, they're going to lose a bit of speed and give off a photon. These photons are the X-rays that are given off by this sort of interaction between the electrons and the surface. So the last one we're talking about, the photoelectric effect, shine light into a surface, get electrons out. Here we're shining electrons into the surface, getting light out. So it's kind of the opposite, but with stacks more energy. Okay, so using this idea, you can see that photon 1 and photon 2, in this case here, if we ignore the heat and whatever that's going to be generated, those two photons should add up to the amount of energy that this electron had as it whizzed through this electric field. So let's say, for argument's sake, that we made this 50 kevs, 50,000 electron volts, 50,000 volts, which means these get 50,000 electron volts each, and this guy here was 30. This one here has to be 20. Alright, so as long as those two don't add up to more than the energy that you put into the system, then we're all good. Alright, quite often it's below, simply because of the huge amounts of heat. Now, there is going to be one single photon that, which one can I make it? I'm going to make it a new one down here. This photon can go into and hit that nucleus dead on, or hit that atom straight on, and completely stop. And if that happens, we get all of this energy given off as one single photon. And that photon is F max, so it's going to have the maximum energy, therefore maximum frequency. So we can look at F max equals E delta V on H. F max is E delta V on H. Now, in the curriculum statement, it says you have to be able to derive this thing or justify where on earth it came from. So going back a step, we can see E equals HF. That's the energy of a photon. So the maximum energy is going to be related to the maximum frequency. Now, the energy in our system is Q delta V, or in this case, E delta V. So the electron gains all of the energy from the potential difference, 50,000 electron volts in this case, and all of that energy gets turned into one single photon. So we can rearrange this guy here to get F is E on H, and for F max is when E delta V, all that energy turns into one single photon. So that's kind of the justification or the thought process or the explanation behind why. Now, just so happens that when or if this electron strikes this, or strikes an electron that's attached to this nucleus here, or this atom here, what will happen is that it will have way too much energy for that electron that it hits to be able to stay in orbit around that thing. And what that means is that you have an electron comes in, knocks another one out, and kind of ionizes that, and it doesn't always knock the covalent one, doesn't always knock, sorry, the valence shell electron, doesn't always knock that one out. Generally it'll knock out one of the ones that's closer in, or somewhere in there. And if it knocks out one that's, in the third orbital, for instance, then, or the second orbital, for instance, what happens is you have this cascading effect where electrons from outer shells or outer orbitals will actually drop down in, and as they drop down in, that they don't have as much energy to keep them at that high orbital anymore, so they've dropped down, they've given off extra energy, and that extra energy is unique to the target material that you're using. So tungsten will have its own, aluminium will have its own, magnesium will have its own, and those are the reason we have specific characteristic peaks, and it's because these electrons got knocked out, and there's characteristic or unique energy levels in atoms, and that electron from further out will be taken away, so it has one from above it will drop down into that shell to take its place, and that dropping down gives off some energy in the form of these characteristic peaks. Now, in an X-ray tube, we have a couple of things that we can control, or a few things. We can control the target material. The target material will sort of define or pigeonhole, there's another word, I can't think of it right now, will give us a specific range of X-rays that it likes to give off, kind of like, they've all got their own characteristic sort of bands, and it depends on what you're X-raying as to what you might actually use. So if it's something like scanning food products, which, thin layer of chicken breast to see if the bone's been taken out, or fish or something like that, you might use aluminium or magnesium. For the human body, you might use something like tungsten, which can generate X-rays that have got a little bit more in terms of the maximum frequency. So we can change the target material. Now, because this target material is getting struck by a whole stream of electrons and there is so much heat, we need some way to cool it. So sometimes a lot of the time it's just like fins and whatever, so you can make it act like a heat sink, so it'll take away a lot of heat. Other times you can have them water cooled or oil cooled or something like that, but there needs to be some way to cool these things down, because all of these electrons hitting the target will actually heat it up incredibly, and you can obliterate the target material completely from the surface, and then it's flat out useless, really. Other things we can do, we can change what's called the filament current. Now, the filament is, just like it says, it's a filament, and it will produce the electrons that are going to be accelerated across the evacuated tube. So obviously this whole setup is in a glass evacuated tube type thing, so that electrons won't bounce into air molecules and hit them and ricochet and lose energy and stuff. So if we change the filament current by winding it up, what that means is we're going to get more electrons coming out, which means we're going to get more X-rays. All right. If we wind it down, then we're going to get less electrons, therefore less interaction on the surface over here, therefore less X-rays. All right, this might be useful if you are you have a small child in pain, they've broken their ankle, and you want to get the job done nice and quick, so you might wind the filament current up a little bit. It could be that you have a patient who's had lots and lots and lots of X-rays in the past because they've had surgeries and whatever. You might wind the filament current down, so you've got less chance of doing damage to their soft tissue and stuff with the electrons as they interact. The other thing that we can change is this guy down here, the potential difference. So if I have this higher, my electrons are going to go faster through here, and therefore the maximum frequency is going to be bigger because my potential difference is bigger. The maximum frequency is bigger, it's going to have more energy, it's going to penetrate through more stuff. We call them harder X-rays because they have more penetrating power, they'll be able to go through stuff. So if you were doing an X-ray on, say, my hand, you might have this lower than 50,000, for instance. You might have it about 25 or 30,000, and that'll be enough to get through the tissue here. But if you're doing someone's thigh or a chest X-ray, there's a lot of material through your rib cage and lungs, and a lot of whole heap of tissue and stuff going on. So this might be closer to 250,000 depending on the person, and that's in order to get a nice bit of contrast. So remember that you have this sort of Bremsstrahlung thing here. So not every X-ray that comes out is going to have the same same hardness or same penetrating power. Some of them are going to be attenuated, so that's the stopping of them. Some are going to be attenuated easier down this end, and some are going to take a little bit more effort to stop. What that means is that if you have the person somewhere about there, that's the thigh, you have the thigh needs, something like this, a frequency of about that much. You wind this up to, let's say, 250,000 electron volts, and then you're going to have some that have the potential to have 250,000. Most are around about, sort of in this sort of ballpark, and then you have some down here. What that means is that you're going to get some that penetrate through, some that don't. So you're going to have a whole bunch of contrast. And that's useful because the contrast is what lets you see the breaks in the bone or the damage to lung tissue or whatever it is that you're looking at. So you actually want lots of contrast. So an X-ray tech's job is to match the filament current with a potential difference for a specific situation, so that you have a patient who has a minimal amount of X-rays, a minimal amount of time in discomfort, but also the best contrast available, so that the specialist can actually see what they're looking at clearly and make a valid diagnosis or whatever it is based on that sort of stuff. Not just used with the human body. Mag wheels, when they're built, they'll actually X-ray them all to see if there's any voids in there. Food products, a lot of that is X-rayed, so that you can't, there's no contaminants and things like that in there. All right. So by now you should know how a Mayan X-ray tube works, and how to spell this word up here.